My name is José Sérgio Almeida. I'm from the Brazilian National Institute for Space Research, INPE, from São José dos Campos, São Paulo, Brazil. And today I'm going to talk about spacecraft environmental tests.
Okay, let's talk about thermal vacuum tests. Once more, these are very, very critical because they have to prove that the spacecraft will survive and operate properly under the harsh of the high vacuum condition of space and the extremes of high and low temperature they can face during the orbital condition. So typically the objectives of the test we can divide in the qualification model and flight model. In the qualification model, we do this test to qualify the spacecraft thermal design. So the guys that work with thermal design and computer, they need to test spacecraft and compare the results we get from the test with the numbers they got during the design phase. So we have to do the test for that and get the numbers for those guys. Also, we have to verify the performance of the thermal control of the spacecraft. Thermal control of the spacecraft, you can have a passive and active one. So the passive ones are typically just we install tapes on the surface, we do some paintings in certain parts of the spacecraft, and they can reject or absorb the heat from the sun more or less. So the designer selects with the most appropriate for each part of the spacecraft, the external surface. This is the typical passive thermal control spacecraft. The active thermal control spacecraft, we have to do something to keep the spacecraft warm or cooler. For example, the batteries. The batteries are very sensitive to the temperature, to the thermal conditioning. Typically, batteries, they don't like to operate below 0 degree. And the spacecraft, very typically, they can go down to -20, -30, -40 degrees Celsius. So what we do, we install around next to the batteries some kind of heaters. They are called skin heaters. They are sheets of electrical heaters. They are attached to the batteries and they're connected to the computer of the spacecraft. So once the computer keep reading the temperature going lower than 0 degree, they start operating, powering up these heaters, and these heaters will maintain the minimum temperature of 0 degree or a little higher in the batteries for the survival of these items. So we call this active thermal control of the spacecraft. We have to provide some energy to make sure that part of the spacecraft will operate in the proper range. Also, in this qualification model test, we can provide information, additional information to the design of spacecraft because we obtain data from the test. So they can get the data put inside the modeling and have a better, more accurate modeling of the spacecraft with the new data collected from the test itself. Now on the flight model again, because we are going to do another spacecraft as a flight model, we have workmanship of the spacecraft, and also we use materials again. So producing the material like resins and operating technicians build the spacecraft, they can do something different sometimes, even follow the procedure of the building of satellite. So it's important, it's good to check this as well because it's handmade, it can present some error or the materials can be changed for some reason during the preparation of the material, the resins, for instance. And also in this test of the flight model, we are going to confirm the proper performance of the electronic operation under the stress of high low temperature and high vacuum as a system now. We can confirm that proper operation. Also, because we are performing a test inside the high vacuum chamber, we are going to verify any possible event of contamination. Some materials, when exposed to the high vacuum, as I said before, they release material, and these molecules can be condensed in certain critical sensitive surface of spacecraft like solar cells or optical devices anyways. So we want to make sure there's no significant amount of release of contaminants from the spacecraft or around spacecraft to be condensed in another part of the spacecraft. We can monitor that, make sure this is not happening. Could be jeopardize or give a problem to the spacecraft while in space. So what's the setup of thermal vacuum test? So here we install temperature sensors because we want to measure temperature in spacecraft. We install, let's say, thermocouples or RTDs. Typically we can install up to, let's say, around 800 sensors in a flight model spacecraft, all in very critical and well-defined points, nodes of the spacecraft that those guys from modeling, they want to compare with their results from the computer modeling. They want to know exactly that point temperature during the thermal vacuum tests. So the spacecraft is put inside a space simulation chamber. I'm going to show a picture in the next slide. So sometimes you have to install like a radiation plates, cold plates to withdraw heat from the spacecraft, infrared lamps or cowl rods, all to produce or withdraw thermal condition from the spacecraft in certain part of the spacecraft only. Sometimes you have to put this in there as well, like radiation source or heat sink next to the spacecraft. And then finally, all the cabling coming from the spacecraft for the sensors or other equipment, they have to be attached to the data acquisition system and to the EGSE, electrical ground support equipment, because during the test, high temperature, low temperature, actually the spacecraft will be operating. So the guys from the laboratory, they install a large amount of equipment. We have umbilical cable connected to the spacecraft, and during the high temperature and the low temperature, the spacecraft must be operating to ensure that it's operating properly in the high and low temperature conditioning and under high vacuum. So the sequence is like that. Typically, first of all, we go for high vacuum conditions. That means 10 to minus 3 Pascal or 10 to minus 6, 10 to minus 7 millibar. That's what we use in typically all the laboratories in the world, 10 to minus 6 millibar. And then we adjust the map of temperature on the chamber shrouds because we want to reproduce the condition of the heat on top of the spacecraft and sometimes the cold conditions that will cool down the spacecraft. And then typically we do thermal balance test and then thermal cycling test. This is the most typical situation, or one of the most typical situations. So in the thermal balance test, what we do, we apply the predicted thermal loads on spacecraft. It's like the flying spacecraft. We see how much power is arriving in spacecraft in hot case and how much withdrawal of energy, of heat, it takes place when the spacecraft is on the eclipse mode. So we reproduce this condition on the spacecraft and we measure with the temperature sensors the result of the spacecraft in terms of temperature. We input the conditions and get the results of the spacecraft in terms of temperature. So these results are going to be compared with the thermal modeling in the computer. The guys want to know if they did the right modeling. Typically 3, 4 degrees, 5 degrees a maximum can be an error, so it's acceptable. But normally it's 1 or 2 degrees only. Nowadays, the thermal models are very precise, thermal modeling. Normally, we got very close numbers compared to the numbers they got in the computer. But we have to do the test to prove that. Otherwise, it's not qualified for flight. Now, in the thermal cycling test, it's a little bit different. Here, they want to check the performance of the electronic equipment inside. Here, we impose the highest temperature on the spacecraft. Stay there for hours and days, keeping that condition. And the guys that build the spacecraft, the guys from the electronic part spacecraft, they actually operate the spacecraft in that high temperature to prove that in that thermal condition, high temperature, the spacecraft will operate properly according to expected. Then we from the laboratory, we decrease temperature, but lowest possible temperature is going to face in space. Let's say minus 45, minus 50 degrees Celsius is the internal part spacecraft. Although the external part like solar panels can reach minus 100 degrees Celsius, but most of the internal part of the spacecraft will be around minus 40, minus 45 sometime, depending on the spacecraft. So we put the spacecraft in this kind of temperature, the low temperature, and again, stay there for many hours or days. And the guys that build spacecraft, again, we operate their equipment to make sure, to prove that their equipment As an integrated system, as a spacecraft integrated, will operate properly. They have to prove that. The spacecraft must finish the thermal vacuum test with the confidence that all the equipment will operate properly under high vacuum and high temperature and low temperature. These are typically thermal cycling tests. We have to prove the spacecraft will operate properly during these conditions. Okay, here's a picture of the spacecraft inside the thermal vacuum chamber, space simulation chamber, located at INPE in São José dos Campos, Brazil. You can see here in the left, we show with the red arrow in the top, showing the thermal shrouds that is conditioning to high and low temperature. I can see here -196 to +150, using nitrogen to reproduce this high and low temperature. When I need to put high temperature on the spacecraft, typically I put high temperature on the shroud, and the shroud will emit radiation to the spacecraft, will warm up the spacecraft. When we want to go low temperature, we cool down the shroud using the liquid nitrogen down to -100, -150 or so, or still lower if you need. And then we cool down spacecraft in the temperature number or level we need to test the spacecraft. Okay? In the right and the bottom, you can see written EGSCE. There is the place where the people that build the spacecraft, the electronic guy, they put their equipment that is going to talk to the spacecraft through umbilical cables. So you have a lot of cables coming from outside the chamber to the inside the chamber through special feeding through the chamber, so they can talk, they can communicate, they can operate their equipment during the thermal vacuum test. This is very, very important to prove you operate properly. Okay, this is a thermal vacuum test. Of course, you close the chamber, make high vacuum, start the thermal test. Here I can show you this next slide some graphs of the thermal vacuum test made in this particular spacecraft. The top one shows the input on the shrouds. You can see sometimes you put high temperature, another time you put lower temperature. This is a long test. This particular one took 20 days, 24 hours around the clock. It's typically like that. The lower graph shows the response that was read in some of the thermocouples installed in spacecraft. Here, only 3 thermocouples from the 800 thermocouples installed. So you can have all the curves of the inputs of the thermal condition and also the response that the thermocouples can read from the spacecraft structure and critical points as we install the temperature sensors. Okay, other measurements and verification that can be done in the spacecraft during the environmental tests and qualification. Like the leakage tests. Because the spacecraft, they have propulsion systems, fuel tanks, pipeline, valves. Obviously, they must be hermetic because otherwise we lose all the fluid inside. So you have to do a leak test on those tanks, on the pipelines and valves as well. So for these tests, the propulsion system is pressurized normally with helium. Helium is very low mass 4, so they are easy to leak if you have a small leak, so use them, and easy to get in a mass spectrometer, so use them to check the leakage, any possible leak on these fuel tanks, pipelines and valves. So we put spacecraft inside the vacuum chamber, the space simulation chamber, so you get high vacuum and you do a global leakage. We can measure the rate of the helium coming out of the spacecraft using a mass spectrometer. If we had any, normally we expect to have known leakage at all, of course. So this is we call global leak test, because we do the test, we can get some noise, some signal, some leakage, but we don't know from where it's coming from. So after the test, if we got some leakage from the spacecraft, we again pressurize the spacecraft and we go point by point sniffing those critical points to see if we can determine which points are leaking, and then we can correct, of course. We call local leak tests. We go point by point with a sniffer, reading any leakage of helium in that particular point. We put the probe, right? Another important test we have to do in this campaign is to check the correct deployment of the solar array. So for this purpose, we have a large structural laboratory, put the solar array in there. We fire the pyrotechnics that hold the several sections of the spacecraft together, like a folded condition, and then by spring and hold by some springs and rails on the top, the solar array will deploy in this system, so you can check if there's no constraints. So if the solar array can deploy properly, all the parts of the solar panel can deploy like in several 4 or 6 meters wide and length. So you can do this in laboratory as well to check the deployment of the solar array. This is very important to make sure there's no constraints on the hinges of the solar panel, because it's full condition during the launch phase. Here in this slide, I can show you a typical flowchart of test campaign of a spacecraft. This is very typical. Like from the top left, the spacecraft arrived at the laboratory, and then we go for EMI, EMC tests, electromagnetic interference compatibility tests, and then we go for the first alignment verification of the spacecraft after arrived in the laboratory. Before going to the test, we do alignment measurements, verification. Then we do the mass properties of spacecraft. We measure the mass, center of gravity, moment of inertia, for instance. We do there. And then we do a solar array deployment verification in this part of the test campaign, before vibration tests. And then we do vibration tests and acoustic tests. So both are vibration tests. One from the shaker, another one from the acoustic waves. And then after the vibration acoustic test, we do another check of the solar array verification, because solar arrays are very sensible to vibration tests. So we do one verification before or prior to vibration, another one after vibration test to verify if we had any problem with the solar array. After that, we can go for thermal vacuum tests, and then, as I said, we do some leakage tests after the thermal vacuum tests, and do again a final alignment verification. Why? We can compare with the first alignment to see if anything has changed during the vibration and thermal vacuum tests. Finish that, we do the packing and shipping to the launch site. So the spacecraft receives as a kind of a stamp from the laboratory, is ready to launch, ready to fly. So just take to the launch pad, put inside in top of the rocket and launch it. Okay, we still can have some variants. Why? Variants is the sequence of testing. According to the spacecraft mission, according to the design of any particular spacecraft, according to the payloads and service module particularities, maybe sometimes, or even the capability of the laboratory for testing. In other situations, there is always a possibility that we have some variants on the kind of spacecraft models, and also on the sequence and kind of environmental test to be performed, okay? But typically, mostly, that was a very typical and classical sequence of testing as I showed you at the moment. So that's it. Thank you very much. So I hope you enjoy this lecture.